Kia ora. My name is Ian Dickey. I'm going to be doing a quick little module on data sheets. And data sheets are, of course, important because that's the start of science. That's when we start actually recording what we're seeing in the field, and that's what gives us the data we need for every subsequent step of our research. And people have been recording data for a long time. There's a papyrus record here from 2500 BC, which is basically a data sheet. People have been recording things, the number of pots they've made, the number of workers building something, since time immemorial. In fact, that's the oldest piece of papyrus that's ever been found, and it's a data sheet. It's recording data. They may have carved it in stone. You might today be recording data on your modern tablet, but it's all still the same idea. You need to have good data management. And so what this talk is going to be about are the principles of a good data sheet. Now, I've just made these up based on my own experience, so if you think I've missed some or want to add some, we can edit this for future years. But here are the 8 things that I came up with based on my experience. First, major principle is to have one. Data sheets are really important. You might think, oh, I'm just going to write down what I'm going to see, and sometimes that happens. This is some data we collected. We didn't expect to be collecting it, so we were just writing it down on a sheet. But there's a cost to that. If we had used a data sheet would provide uniformity over time, so that when you start the day, you might be recording one set of information. You work outside in the sun all day, or you're working in the lab getting really tired. You stop recording everything in the same way. A data sheet tries to keep you on track. It tells you what you need to record so that what you're doing at the end of the day is the same as what you're doing at the beginning of the day. It reminds you, and it does that by reminding you what it is that you need to record. Because you have that data sheet, it also means that if something's missing, you can kind of interpret that missing data as being more meaningful than if it just wasn't written down in some handwritten notes. A data sheet avoids repetition. You don't have to keep writing what everything is, like percent signs. You don't have to write the units. You don't have to write, GPS is this, liter is this, because that will be printed on your data sheet. And lastly, it will make it a lot easier if you use a data sheet when you go to enter that data later. You'll be able to follow a standard format when you type it into the computer. And so rather than something like that, where it's just handwritten, you can come up with a data sheet, like above my head, same exact information, but written in a more consistent way. And you can imagine that'd be much easier to work with later, because you know where to look for each piece of information. So once you have a data sheet, what are the other principles? Number 2, every cell or every column of data should have only one type of data, which means if it's recording heights, they should all be heights. If it's recording diameters, they should all be diameters. You shouldn't be mixing up different things. So if something's missing, like let's say you're measuring the height of individuals and one of them doesn't show up, or one of your subjects has died, one of your plants has died, whatever you're trying to measure, if something's missing, write NA, because that's okay to put in. NA just means missing. And use the notes field. Have a comment field for those things like, oh, it's dead, this one's sick. Don't mix it up into your actual data fields. That becomes really important later on because of the way that the analysis software is going to interact with your data. Also, only have one observation per cell. So even if for example, one thing we see in measurement of plants is sometimes there's more than one stem, and we might have 2 heights where most of them have 1 height. You should always be looking at using multiple rows of data rather than putting 2 different heights in the same cell, because of problems that you'll run into downstream. You really need to keep it one piece of data, one type of data in each cell, one observation per cell. As part of that, when you enter that data, this is my 3rd principle, use only text. That is letters and numbers. Don't do this. Don't do what this person did above me. Don't use color, don't use formatting, or any other way of trying to store information. If you are using electronic data sheets, don't use the comments function. Make sure you've got a cell for a description or a comment that you type it in. Those are really, really important, again, because that information in the colors or in the bold or in italics above my head, all these different formatting things going on, none of that is going to be translated when I try to read that data into analysis software. There's no way to save that information that's in the different colors or formats. The other one, and this can be really, really bad, is you need to avoid any symbols that are not normal characters or normal letters or numbers. Macrons, accents, degree symbols, those can cause problems in corrupting your data file as you're trying to read it into other software. Now, ideally, you would never use Excel for data. Excel is a terrible program. It's also an easy program to use, so a lot of people like it. So if you are going to use Excel, you need to work around a couple other things. There are certain things that if you type them, Excel tries to change what it is. So if you type bracket, C, bracket, Excel will try and change that to a copyright symbol. If you type 3 dots in a row, 3 full stops, it'll try to change it into ellipses. And if you try to use inverted commas, it'll curve them, it'll turn them into smart quotation marks. All of those cause real problems as you try to move your data into other software. But the most insidious problem, the one that you really need to watch out for, is don't use anything that Excel thinks looks like a date. And this is a huge issue. In fact, just about a couple years ago, they had to rename a whole bunch of genes because the gene names, when they were entered into Excel, were being converted into dates. And that conversion is unfortunately a lossy conversion. It actually causes you to lose the original data when it does that. So basic message is don't use Excel, but if you do use Excel, then you need to be really aware of that problem with what you type in might get changed by the program. Principle number 4 is provide good metadata. So what does that mean? Metadata is information about the experiment, the site, or the methods. So this is a data sheet from one of my experiments above me. And you can see at the top, it's got the name of the experiment. It should have somewhere a date that the measurement was done. It's got a list of the team that was on the site so that if there's any questions later, we know who took the data. It's got, if you look just right there, you can see that it gives you the units. So it says, measure the depth of the soil to the nearest millimeter in this case, measure the diameter of trees to the nearest centimeter, the height to the nearest meter. So putting the units in the column headers is really useful metadata. You might also want to, you should have a sheet of protocols that explains what each column represents. That might not be on your data sheet, but it might be on a cover sheet that goes with the data sheets. And lastly, as you're thinking about metadata, think about all the information that might be useful to have later. So in this case, our sites were really hard to find. We knew we had to get back to them. So we have a big field for writing what's the approach to the site? How do you get there? And a spot to put a map so you can actually map out any tricks about how to access the site. It might be different for you what metadata is valuable, but always having some area on your data sheet for notes about the site or the subject or anything unusual could be very useful downstream in understanding your data. Principle number 5, and this is a nice trick, particularly if you're doing weighing of samples where you know what samples you're going to have, is to pre-print as much information as you can. So, for example, this is a data sheet where we actually knew almost all the information. We knew we had certain wood discs. They had a metal tag on them with a number. We knew what treatments they had had. And then we wanted to just record what location they were placed in. And then it's a little bit messed up because we have 2 things in one cell, the location and then the depth. So we recorded just that piece of information. Now, having a pre-printed sheet like this meant that if we messed up and recorded information in the wrong cell, we would pick it up later because we would say, oh, wait, we've already got something here. Well, sample 25B18, maybe we suddenly get something else that should go in that spot, and you can correct it. If you right at that moment in time, you can correct when you've put the wrong data into the wrong field. This really comes into like weighing. So say you've got 300 samples you've got to weigh. If you've got a pre-printed data sheet, you get to a sample and you've already filled in that cell, you'll know right away that you've put that original data in the wrong place. If you just write down the ID and then the weight, it may seem really easy at the time, but later on you go, oh wait, I wrote down the same ID twice. There's no way to correct that. That becomes two pieces of data that are both lost, that if with a pre-printed data sheet, you wouldn't have had that problem. Now, data sheets are tricky. They're not, you think, oh yeah, it's easy. They're not. You need to think through the right order of what things should be where, how much room the data is going to take, what notes you might want to record. So try to do a trial run. If at all possible, take your data sheet out. Even if you can't go to your research site, just do a spare plot, like use the creek behind the building, the field, whatever. Get a friend to serve as a subject, whatever you're doing that you can, that needs measuring. Do a trial run with your data sheet and make sure that it's actually going to work for you. This is an experiment we were doing where we just went out in a grassy field and measured a plot. And that was all about working out our protocols and working out our data sheets to make sure that they worked. Once you're out in the field with your data sheet, be tidy. And that actually involves good design of your data sheet. It means making sure the cells are big enough so that if you make a mistake, you can neatly cross it out like I show above, and write in the correct value. It also means leaving spots for notes. And if you do get a problem, you should try to resolve it right away. Like if you recognize that you missed out a data field that should have been there, you can add a column by hand if you have to. But don't try to avoid putting things that should be data into a notes field. I'll give you an example of that. I was involved with measurement of carbon across New Zealand. I was helping clean up their data after they had taken it. They had thousands and thousands of observations of trees, tens of thousands. It was just pages and pages of data. And they had forgotten to have a field for whether the tree was living or dead. So they wrote in the notes if it was dead. Now with thousands and thousands of observations, there's no way you can go through by hand and pick out all the notes of which ones are dead. So you can say, oh, anything that says the word dead must be a dead tree. But no, because sometimes the comment would read dead at the top. And if it's dead at the top, that means it's alive. Or not quite dead. Or the main trunk is dead. All those things mean that the tree is actually living, not dead. And so we had to write all this computer code to try to go back and see all the different ways that you could say something was dead, all the different ways you could use the word dead, but not really mean it was dead. It took a lot of work. That wouldn't have been a problem if they just added one cell in the data sheet, living or dead. And they could have just ticked one or the other. Problem would have been solved. So try to make sure that if you see something like that, oh yeah, we need to record whether it's living or dead. Don't just carry on and try to fudge it. Fix your data sheets. And the last one, and this is really about, once you have your data, is that raw data is sacrosanct. It's absolutely the core, the heart blood of science. It's what you need to get your master's thesis at least. And so treat it with real respect. Back it up, first of all. If you're taking paper notes in the field, make a digital copy, pull out your phone and photograph that data sheet every single day. If the weather's really bad, you're worried about blowing away, photograph it twice a day. If you're doing digital data, you're actually taking a risk, because if that digital device breaks, are you going to be able to recover your data? So print a copy, email yourself a copy so that it ends up in the cloud, or have a different way of always having some backup of that data on a day-to-day basis, even on an hour-to-hour basis. And I would say you should always be printing paper copies, because electronic data sooner or later gets lost or corrupted. Paper copies, we've got a 5,000-year-old papyrus scroll. We can still read a lot of that data. So paper copies really are good. If you are saving in digital format, make sure you're using a universal format like CSV files, comma delimited files, because that should be readable by any software in the future. Excel is a private company, may or may not be readable in the future. Once you have your raw data, that file should never be changed again. So your raw data should stay as a raw data file. If you need to correct anything, you realize you've made a mistake in the data, that should really be dealt with in a comment in a correction file or in your code that you're using to analyze the data. You shouldn't be going back and manipulating the raw data. And also, don't do what the person above me does. You see this a lot in Excel where people enter the data and then they start doing analysis, calculating means, calculating variances, sticking graphs in right with their data. That's really bad practice. You should be keeping your raw data as apart from any analysis, just saying, here's the raw data, these are the facts, and then separately do your analysis. So that's it. Those are my 8 principles of good data sheets. Have one. Only put one type of data in each cell. Use only text, letters or numbers, no formatting. Provide good metadata. Pre-populate your data sheets when you can. Do a trial run. Be open to changing it if you need to. Always be tidy with it. Keep it nice and neat. And once you have that raw data, it's precious. Keep it clean. Just a couple other really quick tips before I leave you. You don't have to do this all from scratch. In fact, it's better if you don't. So before you get too stuck into making your own data sheet, see if somebody else has used one previously, and particularly look for national standards. So for example, for vegetation data, New Zealand has a National Vegetation Survey data bank that not only collects and stores the data, but also provides you with suggested protocols and data sheets. They're already pre-made and you can just download them. Even if you end up deciding it's not quite the protocol you want to use, it gives you a good spot to start from. So talk to people, maybe talk to your advisor about what data sheets might already be out there that you could use. I haven't talked at all about whether you should be doing this on paper or on a tablet or on a computer. And that's up to you. That depends on your circumstances, your type of data. But if you do use paper, try to get some of this Write in the Rain paper if you're doing any field work. It's a waxed paper that you can write on with a pencil. It'll actually protect your data and allow you to keep taking data even in a pretty bad rainstorm, which is good. It really makes your data quite robust. Even so, make sure you're making if you are using paper, you should be making a digital copy every day. Cell phone photographs work, emailing yourself a copy works. If you're doing digital data, just make sure your data format is a universal format that any software can read. I really suggest printing copies so you keep a physical copy. And if you are taking digital data in a lab, make sure you talk to the lab manager about the safety rules of computers in labs. You need to we'll have to have a keyboard mat to seal off any holes, or they may have other guidelines for you about what's acceptable in your lab space. So to complete this module and tick it off as completed, what I want you to do is think about your own experiments, what you're going to need to measure, and design a data sheet that would allow you to complete that measurement. Take your data sheet when you think you have it ready and share it with another student. Get their feedback on what you could improve in your data sheet to make it easier to use. At the same time, I want you to provide feedback to them on their data sheet. So just back and forth there. And then once you've got a solid draft, you think you've got a pretty good idea of what your data sheet will be, share it with your thesis advisor, and they'll tick off that you've completed this module. And with that, best of luck on your data collection. I hope this was useful to you, and we'll talk to you later.